Okay, so this is Matlab 3. The first question asks you to find the transfer function of this circuit here. And so we can do that by using the voltage divider and the impedances. So we take the impedance of the resistor, as we have ZZ, over the total resistance, or the impedances. So since these are in series, you add them all together. And then when you substitute, the impedance of R is just R, shown for the numerator and over here for the denominator, and then the impedance for the capacitor is 1 over CS, S being the omega J, and LS being the inductance, and then S being omega J again, and it reduces to RCS over LCS squared plus RCS plus 1. And that's the answer number 1. Number 2 says from the transfer function you obtain in part 1, obtain the natural frequency, damping ratio, and quality factor. Okay, so our natural frequency is going to look like this, with natural frequency squared equals 1 over LC. So you could just do the square root of LC, it gives you natural frequency. And then here to find the damping ratio, it's 2 times the damping ratio times omega, or the natural frequency, equals R over L. So by way of do some algebra, you'll be able to find that. And then quality factor is Q equals 1 over 2 times the damping ratio. Okay, number 3 is use L equaling to 1 micro and decide the values of R and C to satisfy the design criteria. Set the natural frequency to be equal to the center frequency of the radio station. Okay, and so Q equals center frequency over frequency bandwidth. The center frequency is 89.7 times 10 to the 6th, and frequency bandwidth is 200 times 10 to the 3rd, which is given in the problem statement, and that gives you 448.5. But remember from question 3, Q also equals 1 over 2 times the damping ratio. So we can get the damping ratio to be 897, and then plug that back into this problem here, which is this. So 2 times the damping ratio times the natural frequency, which we were told is the center frequency, equals R over L, and L being 1 times 10 to the negative 9th. R gives you 160.9. And then using the natural frequency equation, we get natural frequency squared equals 1 over LC, and that will give you C equals 124 microfarads. For number 4, you have to draw the Bode plot for part 3, and that is going to look like this right here. So it increases in magnitude from about negative 35 to 0, and then back to its original, while the phase goes from 90 to negative 90 over a span of 10 to the 15th. And then number 5, is also draw the Bode plot when you increase R by 100 times, and that will look like this. And basically it's the exact same. I know it's hard to see the units, but it just essentially stretches out the Bode plot so that it stays, for the magnitude, it stays at 0 longer. So here we can see this is 10 to the 15th, and so on the original one, 10 to the 12th would be at like this area, on this would be this area here, and it's curved, where here it's at 0, and then 10 to the 12th here is about 0 also, where in the original one it's about on the slope. Okay, and then we have number 6, which says determine the filter you designed is stable or not. So we do that by basically solving this equation right here, which was our denominator, if you can remember, and a system is stable when it's negative. So if we do this, you get 0 or you get negative. Well, actually, you don't really get 0, but it's a number negative really, really close to 0. And then you get negative RL for the other one. So it is definitely stable. And then for 7, I had it done, but since the numbers changed, I didn't show it. So I'll move on to number 8. So for number 8, basically it gives you a high pass filter and a low pass filter, and actually in her diagram it's not correct. It should be the top one should be the low pass filter and the bottom one should be the high pass filter, just from the way they're set up. And it tells you to find the transfer function of each one. So just like we did in problem 1, use the voltage divider and the impedances. So we have ZZ, which is our capacitor in this instance, over Z1, our resistor, Z2, our inductor, over that, and it'll give you 1 over CS because the impedance of capacitor is 1 over C, and then it's R LS 1 over CS. So this reduces. Better to get it as 1 over, so you can find the magnitudes a lot easier if you were to do it by hand. And then the same thing goes for the high pass filter, which comes out to be this, and it's a high pass filter because if omega goes to infinity, so if our S here goes to infinity, this is going to end up equaling 1, and because we go to infinity and this will go to infinity, whereas up here, if S goes to infinity, it's going to get closer and closer and closer to 0. Or sorry, it'll get closer and if this gets closer and closer to 0, this will go to infinity. So that's why it's a low pass filter. And just like here, if this goes to infinity, it goes to 1. So that's why this is a high pass filter. And then for our Bode plots of this, we have to go to Matlab figure 3, which is the first one. So you can see that it is a low pass filter, and that it starts from 0 and goes to around negative 30, and then the phase goes from 0 to 10 to the 6th. And for figure 4, which is the last one, for the high pass filter, it starts out negative and it's going to get closer and closer to 0. And then the phase, it goes from 180 to 90. And the reason that these numbers are more skewed and about double the other is because of the S squared in the numerator for the high pass filter. And that's why each Bode plot is different in relation to omega, is because the difference between as it goes to 0 or as it goes to infinity, and the results you get from that relationship.